My name is Erik Mueller, and I'm going to be talking about going beyond fact-based question answering. So how do we solve the AI problem? This is the big question. Watson has been hugely successful at answering fact-based questions, like the sorts of questions that we have on Jeopardy. But to solve the AI problem, we need to go beyond simple facts. Examples of hard AI tasks that go beyond simple facts include answering questions about medical tests, answering fourth grade science questions, and narrative understanding tasks like understanding RoboCup narratives, which involves inferring the state of a RoboCup match based on a narrative of that match. So in this talk, I'm going to be talking about some of the systems I've been working on over the last few years. I'll start by talking about the Watson system, the original Watson system for Jeopardy. Then I'll talk about several systems that go beyond facts. First, the Watson for Healthcare system, and then the WatsonPaths system. And then I'll talk about what I think the priorities should be going forward based on my experiences working on these systems. I'm going to talk about the event calculus, which I think is a good combination of features that we need, and talk about its application to fourth grade science questions. So the original Watson Jeopardy system. As we all know, in 2011, Watson won a two-game Jeopardy match against two Jeopardy grand champions. And the Watson algorithm is this. I'm going to go over it because it serves as a good baseline for the rest of the talk. So we start by taking a question as input, like what disease causes right upper quadrant pain? We then perform question analysis on it. We identify entities in relation instances in the question. We parse the question. We identify the lexical answer type and the focus. The lexical answer type in this question is disease. It's the type of the desired answer. And the focus is what disease, which is the portion of the question that if we plug the answer into it, we should get a true statement. So once we do question analysis, we then retrieve documents and passages using various search engines like Indri and Lucene. So we generate a query, and we retrieve documents and passages. We also, at the same time, can retrieve answers from structured sources. And then we will get from passages, documents, and structured sources a variety of candidates, candidate answers. And these are some sample candidate answers coming from various sources with various scores that are produced by either the search engines or the structured sources. We then now, once we have a bunch of candidate answers, we try to retrieve passages that might support those answers. So we create new queries where we insert the answer. Well, we consider each candidate one by one. So for a given candidate, we create a new query that's a combination of the candidate and some words in the question. We then retrieve passages, and then we take those passages and we score each passage. Well, we score each answer in the context of all the passages for that answer that are retrieved for that answer. So, for example, for the candidate cholecystitis, we might retrieve a passage, cholecystitis may cause right upper quadrant pain. And that is a passage that does support that as an answer to the question. Then there's another step, which is to merge equivalent answers. We may have different synonyms, different versions of answers that we can then merge using various techniques. Then we calculate final scores for each candidate.
So, very quick question.
Mm-hmm.
So, what is the notion of support that you're using in that statement that the passage supports that answer?
It provides evidence for the answer being the correct answer.
That's my question. In what way does it provide evidence? Presumably not through predicate calculus.
Right, not through predicate calculus. Basically, we have maybe 20 different scorers that use different techniques. So each scorer has its own notion of what is support. the simplest scores are just looking for similarity in maybe parse graphs and things like that, or just some very simple scores to simply count the number of words that are the same in both. It's not a logical notion. So we get back a lot of scores for answers from all these scores and from our structured sources, and also the original scores that we had from the search engines for each candidate. We calculate now final scores for each answer using a binary logistic regression model that previously was estimated from training data, which is training data, similar questions to the questions that we want to answer. And then we return answers along with their scores. So this is a graph showing how the performance of Watson was driven up over time. And this is a test. We drove it up using a variety of data that we rolled out, but this test was done on a 200-game blind test set that we kept blind for the entire time. And as you can see, by the end, we got to about 70% accuracy. Okay, now I'm going to talk about the Watson for Healthcare system, which is the first system basically after the original Watson Jeopardy system, which is to adapt Watson for the healthcare domain. So what we did was basically two top-level steps are involved for doing this. We first acquired and incorporated medical content, in addition to some medical content that was already in the original Jeopardy system. And then we added new components to help improve the performance in the medical domain. So the first step was to add a bunch of medical content, journal articles, medical textbooks, medical case studies, clinical guidelines, and we also expanded that content by going out to the web to try to find more content that was similar.
When you use the word content, are you referring exclusively to text or also to databases?
Exclusively in this, I mean, I think the concept would probably refer to both, but most of the content that we acquired was in the form of text. Some marked up text with section headers and things like that, but text. So one of the steps that we do in Watson when we are adding content is called content ingestion, and we create things called title-oriented documents. Earlier I mentioned that we retrieve both documents and passages. For Jeopardy and often for a lot of domains, the title of the document that you get back is often a good answer to a question that a query based on that question. So we create title-oriented documents for a lot of concepts. In the case of medical domain, there are things like medical conditions and treatments. And we also annotate the title-oriented documents with the same natural language processing stack that we use to parse questions. So we run the ESG parser on it, we run medical concept recognizers on it, etc. So we then store and index those TODs, and we also annotate and store data for use for the passage search, which is just retrieving small passages of text. So now the second step is.
How big are these TODs? Are they like journal articles or maybe just a paragraph?
The TODs tend to be about the size of a Wikipedia article. Those are sort of actually our best TODs in the system. We have experimented with smaller TODs. It's actually good to have some small TODs because they're very targeted towards something. If they're too long, it's maybe a little less precise.
So the structure of a TOD is the title and the content, or is it further split down into sections or other details?
It's forget the name. It's a format. There's a format, and it is broken down into sections. And we don't use that so much. The sections. there is capability in INDRI to do section-based retrieval, but that's used a little bit maybe when you're asked a question where you're given symptoms and you want to retrieve a disease. One trick is to search only in the symptoms fields of the TOD. So here's a list of some components that we added. There's a database of medical concepts from the National Library of Medicine. It's actually a combination of a lot of databases that they've put together and merged with medical concepts. We recognize medical concepts in the question and convert them into their CUIs, which are their concept unique identifiers. And we do passage and document retrieval by also using synonyms from that. And I also built a structured knowledge base for the medical domain, which was mined from our medical corpus. It used point-wise mutual information to find associations between signs and symptoms and diseases, and between other things too. We added some answer scores. Again, we can use synonyms to do matching in scoring passages. And we can also use those concepts to determine the degree to which a candidate answer matches a particular lat, which is the type of the answer that we want. And we can also use UMLS for doing answer merging. So the question set that we tested Watson for healthcare on is called Doctor's Dilemma. It's actually a competition for medical residents, interns, and fellows. And it's similar in format to Jeopardy, but it's harder than Jeopardy for two reasons. One is that there's more variability in the terminology in the medical domain. Thing like lung cancer, there are at least these different ways of expressing lung cancer. And also some of the questions involve effectively doing a diagnosis from signs and symptoms. So we acquired 5,000 Doctor's Dilemma competition questions from the American College of Physicians. These are some example questions. Diagnosis suggested by hypotension, fever, rose spots, and bradycardia. The answer is typhoid fever. And here's our performance. At the end, we ran a couple of different versions of the system on 188 unseen Doctor's Dilemma questions. The first number here, this is the performance. By the way, this is the accuracy, the number of correct answers. The first row is running the original Watson for Jeopardy system on those questions without any modification and not retraining it. The second row is running that original system, but adding the medical content to Watson.
Sorry, are these four-way multiple choice questions? Or?
These are open-ended questions.
So the answer is a phrase, or it could be an essay?
It's usually a short phrase. It's definitely not as long as an essay. There are occasionally things that are maybe 4 words long or something, but it's usually 1 or 2 words.
So what do doctors get on this task?
Sorry?
What do doctors get on this task? I mean, how accurate are people?
Yeah. I don't know. I think they probably, my guess is they do about 70%. I don't know. The third row is the original Watson Jeopardy system plus the medical content plus retraining on Doctor's Dilemma questions. Finally, the last row is all of the above plus modifications, the modifications that I described, the components we added to improve its performance in the medical domain.
So since these are short answer questions, how do you measure accuracy? Is that a human annotation thing?
We have an answer key that typically consists of about 1 or 2 or 3 or 4 or 5 correct answers. And we have We have a process for vetting answer keys. Because of the medical domains, sometimes it can be phrased slightly differently. I actually don't know if this unseen test was done with a revetted answer key or whether we just kind of used the first pass at the answer key. I'm not actually sure about that. But it's just string comparison between the strings it produces and the strings in the answer key.
Eric, sorry, one more question. You implicitly used the original Watson system as the baseline here. Did you guys try any other simpler baselines?
No. So now I'm going to talk about the third Watson-based system, WatsonPaths, which we applied to the task of answering medical test preparation questions. So WatsonPaths is designed to handle more complex questions than Watson. So Watson, for the most part, performs single-step inferences. The goal of WatsonPaths is to be able to perform multi-step inferences by repeatedly invoking Watson. This is an example of a question that WatsonPaths handles. It's much longer, as you can see, than a Jeopardy question. It starts out with a medical scenario. A 63-year-old patient is sent to the neurologist with a clinical picture of resting tremor that began 2 years ago, et cetera, et cetera. And then it actually asks a question at the end, which is called the punchline question, which is the piece of information that we want to pick out as the answer. What part of his nervous system is most likely affected? And in this case, we do get multiple choice answers given to us. So this is the WatsonPaths algorithm. I'll show an example in a second that maybe make it more clear, but this is basically it. So we take a top-level question as input. We analyze the question by identifying relative medical concepts in the question, signs and symptoms. We then add those concepts as nodes to a thing called the assertion graph, which is a graph of nodes and links. We also add the multiple choice answers to that assertion graph. We then enter a loop in which we're repeatedly adding nodes and edges. So we generate edges by asking Watson questions. So we ask Watson sub-questions and use the answers to generate new nodes and edges. In particular, we ask questions about the concepts in the question, and we also ask questions about the multiple choice answers using the relation expressed in the punchline. I'll give an example of that in a second. And we can also run other edge generators, such as those that are based on structured knowledge bases. We then estimate confidences in the node using Bayesian inference, and we also can perform a step of identifying further hypotheses like diagnoses, although in this case we don't have to do it because we're given the diagnoses, the hypotheses up front as the multiple choice answers. And we do this until some stopping condition is met, and when we're done, we return the multiple choice answers along with the confidences that we've calculated for them. So this is a fragment of an example based on that previous scenario that I showed you. So this is an example of asking a question based on one of the multiple choice answers. So it's what was the original question? It was, what part of his nervous system is most likely affected? That was the punchline question. So here, we ask the question, in what disease is the substantia nigra most likely affected? And Watson will come back with a bunch of answers to that question. And we add them to the graph and link them to this node. So one of the answers to that question was Parkinson's disease, which is actually the correct answer. Now, we also ask questions the other direction. Well, I guess the direction of the link, I don't want to get hung up by direction. unexpressive face is a concept that was in the original scenario. We ask a question about that, what disease causes unexpressive face? And one of the answers back from Watson to that question is Parkinson's disease. So actually we have a nice path here. And when we do all the calculations, that answer will actually get the highest score.
Where do these questions come from?
So we have a question generator that uses a thing called the Emerald, which is a set of, it's all the different types for the medical domain, basically signs and symptoms, diagnoses, and links between those types of things, like a disease can cause a sign. And then we have question strategies that are associated with each link. So if we want to look for links, it's a template-based mechanism. So we just fill in it's what disease causes, and then the node that you.
If there's a disease, you want to know what might cause it, and if it's a symptom, what might it cause, and if it's a location, what disease might be present at that location.
Right. So if given a more complex graph, we may have different types of nodes, and then it can ask appropriate questions between those nodes based on the types of the two nodes, and also what type of link you're looking for. Although I think we mostly have only one type of link between any two types of nodes, typically.
So as you can see, we're fascinated by this. I know you want to get in, but just real quickly, it seems like there's this challenge here from an engineering point of view, right? You alluded to the, you developed the paths, but then there's a bunch of weights, and the amount of data you have for training the weight is non-trivial, but it's still pretty small. So I can imagine all kinds of instabilities and just, pain in the ass, to use a technical term, where you make some changes and then you run it through the weight trainer, and then suddenly it's not working as well and you're not sure why. So I'm just curious, did you just bite the bullet and hope for the best, or were there particular disciplines, methods, tools you used to deal with the weight training issue?
I think that it definitely, one thing we were hampered by is not having a lot of training data. So we would definitely see effects of the sort that you're mentioning. And I think what we got to, our original goal was to be able to answer all types of medical test preparation questions. And we decided to focus first on just the diagnosis ones, because for those, we can limit it a lot more, and we can basically just ask questions from here to here and from here to here. And it gets rid of that problem. But we haven't yet solved the issues with much larger graphs. And we would probably need a lot more data to do that properly. Now, what we did for evaluating WatsonPaths is we evaluated the accuracy. Now, in this case, they're multiple choice questions. So the baseline is about 25%, because they're usually 5 multiple choices per question. We evaluated the accuracy on 500 unseen questions that came from Exam Master and McGraw-Hill. And we compared the performance on Watson for Healthcare System with the performance of WatsonPaths. WatsonPaths did significantly better than Watson for both sets. We evaluated on a full 500 set of all types of questions, and also on a subset of that 500 that were the diagnosis questions. And just to be clear, both systems were retrained on another set of 1,000 medical test preparation questions. So they both were able to be trained for this task.
Do you have any idea if there's a similar precision recall trade-off to what was done with the original Watson for these? Since I assume this is kind of accuracy, giving an answer for every question. But if you allow it to say, I don't know, can you obtain like high precision on some of the questions?
I mean,
As
not
in, I
sure.
would like
Well,
to have a
because
doctor
these are
who'd be confident and say,
Yeah.
maybe I won't do anything.
Well, I mean, of course, we can set a threshold on the answer, but I think in this case it's multiple choice answers, so we're forcing it. It's much easier. I mean, it's definitely one of those 5 is the answer, so it's going to get 25% at least. Okay, and a lot of the focus on WatsonPaths right now is on the interactive part of WatsonPaths. So WatsonPaths is actually a system that's being used by medical students to help them learn about medicine. And one of the features of the front end is also to allow the user or student to teach Watson and WatsonPaths. Some things that we've already implemented are teaching Watson new natural language expressions for diseases and findings, because they're always expressed a different way. It's quite amazing. And also recording how students solve problems using the tool, because they can actually add their own nodes and links to help WatsonPaths out or to just experiment. And WatsonPaths can also be applied to other domains requiring diagnostic inference, and those are being looked into. Okay, so I'm going to talk about what I think are some priorities going forward based on my experience in these 3 versions of Watson. So I think that to deal with...
If students are teaching the system, how do you make sure they don't teach it something that's wrong?
Yeah, our focus isn't so much on... so we don't have any mechanism. In the case of teaching new natural language expressions, we are accepting those. This second thing about recording how problems are solved is more kind of an open-ended thing to understand how humans solve problems, more than the correctness of the particular graphs that they're producing. But as I say, this is in the initial phases. So to deal with the richness of human knowledge, I think we need to move beyond propositional logic and to predicate logic. So as you may have noticed, in WatsonPaths, we're mostly dealing with atomic propositions, and effectively we have implications. So we're going, say, from an atomic concept, circular rash, and from that we're inferring Lyme disease, and then we go, say, from Lyme disease, that might imply a treatment, doxycycline. But of course, for medical knowledge is much richer than that, and it requires connectives. So examples of those medical knowledge involving connectives are rules like these. If someone does not have an enlarged thyroid, they probably don't have hyperthyroidism. That's a negation on both sides of the implication. Here's an example where jaundice and palpable gallbladder implies that someone does not have hepatocellular jaundice. There's also a lot of medical concepts that are defined using connectives. So the definition of dissecting aortic aneurysm is that it's an aortic dissection and an aneurysmal aorta. And they're also, in the medical domain, there are these things called syndromes, which are things that they don't necessarily know the cause for yet. So they're defined as conjunctions or various logical combinations of other things, like this. And of course, in cancer, we have particular pathology, histology that they look for to define particular types of cancer, and et cetera, et cetera. Now, a domain where this becomes very important is the domain of mental and behavioral disorders. So there's this book put out by the American Psychological Association called DSM-5, which lists all the mental disorders, and it provides diagnostic criteria for each one. And they can sort of refer to other a definition of one disorder can refer to a definition of another one. So the definition of panic disorder is panic attack and either worry about additional panic attacks or worry about the consequences of a panic attack, etc., where a panic attack is defined as 4 or more of these things, where some of them are actually ors. So given rules like that and a new case, we should be able to conclude that the person has panic disorder, panic attack, etc. Now, we'll often have, again, in a case, we'll have the way things are expressed may be different from the way they're expressed in the rules. So we have to be able to get from those, between those two things. Dyspnea and shortness of breath are almost synonymous. Worried about going insane, worried about going crazy. We have to have, obviously, some way of realizing those are very similar things. So, but I just think that we need to extract, correct, and refine knowledge in advance because this kind of thing is too complex to be left to chance. Basically, right now, we generate queries on the fly to Watson and then basically rely on what we get back to do all our inference.
Do you attach probabilities to those rules?
I mean, we should attach probabilities to those things, definitely. I haven't shown them here, but yes, or weights.
So there's two notions of probabilities. There's whether the extraction is correct. There's also just is there a correlation. So medical textbooks will tell you high temperature suggests fever, but it won't tell you the probability of correlation rarely will. So getting that statistical information seems important.
Yeah.
Not mineable.
It's hard to mine. There are, in the medical domain, there are two numbers, specificity and sensitivity. The sensitivity is the probability of the finding given the disease, and the sensitivity is the probability of not finding given not the disease. And there are books that have a lot of this data in them, but it's not very dense, and it's not dense enough to really solve actually medical test preparation questions. But maybe, there are maybe ways of backing out those numbers, but that's remains to be seen.
So is there a way that you replace the disjunction somehow with conjunction? This will simplify the representation a lot, right? To replace all the disjunctions that exist here with some sort of conjunctions, kind of change the representation a little bit.
Can't you just distribute the rules and then?
So for example, for the second one, you can distribute the rules, but if there are disjunctions on the right-hand side, it's more difficult, right?
Why do you want to do that?
Because dealing with conjunctions is much easier, right? You can collect data easier and then assign probabilities and those type of things. But
right. I think we can factor out, the disjunctions we can probably get rid of before we do that, because there are variations in the way of expressing things that maybe we can do that at a different level before we start worrying about the probabilities. And obviously, there's a need for arguments. If the question mentions the patient's mother, we have to be able to realize that that's not the patient. That's not the patient's symptom. So the second thing is to deal with the real world, we need to be able to reason and represent events in time. A very simple example, obviously, is if the question says it was jaundice 10 years ago that is resolved, we need to be able to know that the patient does not currently have jaundice. A more complex example might be with, this is a pretty complex example, with a patient who's asthmatic, has bradycardia, which is a slow heart rate, and has a blood oxygen tension of 62. The hypotheses we're given are asthma attack and impending respiratory failure. It turns out that asthma attack actually initiates a fast heart rate, but this low blood oxygen level actually initiates a slow heart rate, which are obviously fast and slow heart rate are in conflict. And But it's actually quite possible that the person first had an asthma attack and then had the respiratory failure. So we should be able to account for that and not just think that this is all in conflict. An example of the need for time is obviously in narrative understanding, such as the RoboCup narrative understanding, where you're given a narrative of of the game, and you have to determine at the end of each sentence who has possession of the ball and did a correct pass happen. And then also a narrative, more general narrative understanding task that I propose, which is to answer a whole mess of questions after each sentence of a narrative text. And third, I'm just wondering what time is it?
It's 10:39.
Okay.
20 minutes.
Okay.
But I think it seems obvious that you need these things, right?
Yeah.
I don't think anybody would disagree. The question
Right.
is, how do you make them tractable or usable, right, without falling
Right.
off some cliff?
Right.
So we're with
Maybe I'll get to that a little.
Well, I would say skip
yeah.
all the part where we need stuff. We know.
Okay. Okay, so quickly, declarative methods. Declarative methods are very nice because instead of writing a program to solve a problem, you can describe the problem and the computer figures out how to solve it. So they're actually great for finding models of narratives, and that's, in psychology, that's the theory of how narratives are understood. You build a model of what's happening in the narrative, and then you consult the model to answer questions about it. Answer set programming is a declarative method where we take a declarative representation of a problem and produce 0 or more solutions to the problem. And there are a variety of off-the-shelf answer set grounders and solvers that we can use. And here's a sort of example of the event calculus and narrative understanding, just showing how multiple models are nice because we keep things separate. So if a person goes somewhere, they either, this is simplified formalization, but if a person goes somewhere, they maybe either run or they drive, and if they run, they get tired. So then we're given a particular scenario, a person is not tired, and then they go to the bookstore. We get two distinct solutions, one in which they drove, and they're not tired, and one in which they run, and they are tired. And again, in medical domain, it's useful for a case like this in which we may be given something like high ornithine, which is ambiguous as to high urine ornithine or high plasma ornithine, which actually indicate two completely different disorders. And again, we can keep those separate. And it also may be useful for math questions, things that involve constraints or finding all solutions to things. We can answer this question easily using answer set programming. And this is another sample question that involves a bunch of constraints that we can solve with answer set programming. And the event calculus is an example of a formalism that embodies these three things. My book, which was originally released in January 2006, discusses it, and I updated it recently. The second edition came out last December. The entire text was updated, and I also added 3 new chapters, one on answer set programming, one on reasoning using unstructured information, and one on knowledge acquisition, and I also added several appendices and sections. So I'm not going to give all the stuff about the event calculus. You can probably imagine how it works, but just quickly, the basic notions are there are events which are instantaneous typically, although you can model events with duration, but we'll stick to the instantaneous events for now. The fluents, which are time-varying properties of the world, and time points. And then the basic predicates are that an event happens at a time point or a fluent holds at a time point. So the event calculus is good for understanding narratives, and 4th grade science questions sometimes contain narratives, like this example. It rained on a hot summer afternoon and a puddle formed. After several hours, the puddle was gone. Which 2 processes made the puddle form and then disappear? The question is, can we use the event calculus to answer such questions? I mean, yes, we can manually code a theory for this, and we can use it to produce produce the correct answers. But as Peter asked me, how do we connect the neatness of the event calculus with the messiness of natural language? So there are basically two approaches to doing this. One is to go for the whole thing, or another approach that I'm going to propose is working one topic at a time. So going for the whole thing is very hard. That would involve translating arbitrary text into the event calculus, mapping states, events, and rules into the various event calculus predicates. It's not completely crazy because there, of course, is related work like semantic role labeling and semantic parsing, but of course the event calculus is a lot more exacting in the form of the representations. There is actually a thing called ping light, which is a controlled natural language for the event calculus that allows you to express both general rules as well as particular scenarios, but it's a controlled language, so we can't use it directly to deal with natural text. So this way of doing it is difficult. It's probably worth doing, but it's more like a 10-year project. That's a difficult way of going about it. So as an alternative, what I'm proposing is a way of working one concept at a time. So the first step is to first identify a set of topics that frequently arise in the tests. And then for each topic, either learn or manually code the following. First of all, an event calculus theory for the dynamics of that topic. Then a classifier to determine whether a text is about that topic. And then methods for mapping text into the appropriate event calculus formulas for that topic. But this is a lot easier problem because we're only dealing with one topic at a time. So what I thought I would do is just start doing this. So I went through the science test from 2004 to 2011. There were 240 multiple choice questions, and I selected those that didn't have diagrams and tables, but did have one or more answers that were events or processes, on the theory that those might be questions that the event calculus would be good for. So that gave me 63 questions. And I looked at those 63 questions to see, I sort of annotated them as to what topic I thought they were. This is how it broke down. Now, some of these topics are not really great topics for the event calculus, like functions. What is the function of x, or something like that. But some of them are good for the event calculus, like water cycle, animal adaptation, boiling. So what I did was I thought I would just code a small proof of concept with three theories. The first one was the water cycle theory. The second was animal response. And I also threw in this boiling theory because I originally had that question as part of the water cycle, but then I realized it needed to be modeled using an event calculus trajectory. So I ended up with that as a separate one. So I built a number of different constraints and rules, which I'll show you in a second. I used the Stanford dependency parser and basically took the output of that parser and converted it into answer set programming atoms that were then in a format that I could deal with in answer set programming. I got it working on the 9 questions, and with those 9 questions, it basically worked. But of course, it's a very small set of theories. So just to be clear, this is not any major algorithm or anything, but just to be clear about what I did, this is the algorithm just looping through the questions, running the Stanford parser on the question, forming a list of answers. So for each microtheory, generating an answer set programming problem based on the dependency parse, the theory, and we're given the question choices also. Then we run the answer set solver on the problem. We get usually one model back, and then we pick out the best answer from the answers that we got, and we basically just calculate our accuracy like that. So now, I think it's interesting that you can express some constraints for this in answer set programming that work out pretty well. One of the constraints I noticed is that we can say this happens L predicate is kind of like a language equivalent predicate to the event calculus predicate. And we're going to define that later with other things. But there's a constraint that events must happen in the model in the same order they happen in language, which is not true in general natural language. But I looked through the problems, and it actually was true for the five water cycle problems. I wonder, it's a conjecture as to whether it's always true in these questions. And similarly, similar rules for fluence. Also, events that happen in language have to also happen in the model. But these may not be the exact ones we will end up with, but these are the sorts of constraints that we can create. Then there are some things for answering particular types of questions. One of the types of questions I notice comes up is what causes. So again, there's another rule that generates this based on the natural language, which we'll get to in a second. But if we have a what causes question, and we know that this event causes that to transition to that, then the answer is that. Now this is an intermediate predicate, which I just define using the more basic event calculus predicate. So E causes F1 to transition to F2 at time t if E initiates F2, E terminates F1, and E happens at that time. These are all at the same time point. And then this is mapping event calculus terms to language terms. So again, we have ways of expressing things in the event calculus which are different from the way we express them in language. And this is turning the event calculus, notice this is generating an answer predicate, which is actually the event calculus predicate here. But we have to have a mapping from that to the one that's used in natural language to actually get the answer. But this answer predicate is the one that the algorithm actually looks at in the model to pick out the final answer to the question. But these are some of the examples of the actual mapping from the Stanford dependency parse to intermediate predicates like happens L. So this may seem far-fetched, turning it rained into precipitate, but actually I don't think it's that far-fetched.
So these mappings were written by hand by
yeah,
you
right.
on the 5 questions?
Yeah. But these are things that we could learn.
So the question isn't whether it's far-fetched. The question is that the problem that you're solving, right, of mapping language to a more formal vocabulary is a problem that's received extensive attention in the literature, and it's known to be error-prone, right? And so this is not a hypothetical question. Hey, we might be able to do this. We know that we can do this somewhat with great difficulty. So the obvious question is, given that for the foreseeable future this is highly error-prone, what happens when you map the output of an error-prone process into the event calculus describing? Doesn't it all just come tumbling down?
I think it does if you stick to answer programming. I think you do have to go to probabilistic logic like Markov logic networks or something like that. But you can still use the event calculus with those kinds of, when you add probabilities, you can still use all the event calculus axioms and they will work. But you will now have probabilities of events occurring rather than just the event did occur or did not occur.
So the broad scheme that you're hypothesizing would be to do that mapping using some learning process based on what's been done in the literature, maybe extended, and then to use some kind of probabilistic MLN or some such thing, but then further constrain or inject the insights from the event calculus into that framework to get more, to get that power.
Exactly, yeah. And I present it this way because I think it's easier to understand it first categorically before you introduce the weights and the probabilities. So just so you can see what that theory looks like, the water cycle theory, it's just this, a simple model of phases of matter and the transitions between those phases. And I guess we kind of saw this before, but this is incorporating all those predicates if you want to see that.
Sorry, just so I understand, are you suggesting that we can learn this whole theory from text as well, or do you need to write this down for every kind of
Well,
situation?
I think so. I think maybe the first place to put the learning in is in the mapping from natural language to the event calculus from the questions. In terms of learning the theories themselves, I think it may be completely feasible to manually code those theories for fourth grade science exams because we have the curriculum documents and the study guides that pretty much characterize the knowledge you need to be able to answer those exams. But then eventually we would of course like to learn those theories, and there are techniques for learning them, but again, they're noisy. So maybe the first thing to do would not be to do that.
With regards to the disappear in the question, that's sort of an example of implicit stuff in natural language. I don't think you'll ever find in any textbook like a statement that if water evaporates, it disappears. How are you bridging such gaps in your model?
Right. We could, I'm trying to remember because I did an earlier version of this where I was trying to learn things like that. We can have annotated data. We're going to eventually there's either going to have to be annotation of these correspondences. We're going to have to learn this from something. So I actually can't remember what some of my ideas were about how to learn those things, but we should find the correlations eventually. Disappear. Evaporate.
I typed water evaporates, disappears into Google. There's lots of examples. Again, I don't know if we could parse them as a sentence, but if you look at the proximity, those water evaporates and that phrase and the word disappears appear in frequent proximity. It's amazing what people will say on the web. No, there might be. I mean, obviously there's a lot of noise. Other things would, but yeah, just different.
Yeah. Okay, so we've touched on some of these things, but to scale this up, we're going to need, obviously for topic classification, we need questions annotated for topic. For learning the mappings, we can use a variety of techniques. We can do supervised learning on that to try to learn some of these mappings. And we can manually code a fair amount of the glue again, since this this domain is fairly circumscribed. But we will need more question data. There are lots of study guides. There are other jurisdictions with similar tests, and we can even author our own questions in the same style. So quickly, if you want to run the event calculus, you can follow the instructions at this URL, and I'll, I guess, get you these slides or something so you can copy this URL. You can download the axiom sets from there, and then you can download the Klingo answer set solver to run them. And these are some of the publications related to this talk. And I'm organizing a workshop at IJCAI 2015 on cognitive knowledge acquisition. And the focus of this workshop is on acquiring rules with arguments, variables, and time. In fact, we'll accept anything that's currently impoverished in current mind knowledge bases. The submission deadline is April 27th, which is coming up soon. And we got funding from the AI Journal for this workshop. So in summary, to solve AI, facts are not enough. We need predicate logic or something like it. We need general inference rules. We need to reason about time. And we need declarative methods of various types. And we can use the event calculus to answer some 4th grade science questions. Thank you.